self-stress and all of that for this one. But now rather than having 2 or 3 dimensions per site, we only have 1 variable per site. So let's, this is the model. Here's the lattice. We have triangles. Now it may look like this is a hexagonal lattice, but really the sites, the various parts are on sites of a honeycomb lattice, as you can see right here. So the blue dot is, of course, the center of mass of the triangle. And it is what we'll call, that is the center of what we call a tribond, right? So we have bibonds, which is what we're used to having for most systems, where we have a mechanical element that connects 2 sites. Here we have a mechanical element whose center of mass is at the blue dot, and it's repeated and repeated. And notice that there is 1 blue dot per unit cell. That the unit cell of the diamond lattice, of the honeycomb lattice, which is that of the graphene, has 2 sites and 3 bonds, I think it is. 1, 2, 3, yeah. Or is it just 2 bonds? I've forgotten. 1, 2, 1, 2, 1. Yeah, just 2 bonds, but 3 sites. So it's not isostatic for if we put in nearest neighbor forces. It's under-coordinated. Okay, so now we have the red sites label the positions of the sites themselves. So the red sites we're going to call the sites, and the blue sites are where the bonds are, the tribonds. And the yellow thing is where what do you call it? It's basically a site where that you could rotate about. I've now forgotten what I call it. It's called a pivot point. Yes, a pivot point. So this point is either attached to a spring or to a point, so that you can only rotate in 2 dimensions about that site. And what we're going to imagine then is that as you distort away from the perfectly flat triangle, which is the tribond, that's where the energy cost comes from. So here, I've just put down these things. We're going to label the directions here, D1, D2, and D3, which we see down here. Going upward is the D1, going to the left is D2, going to the right is D3, and we're going to call the red sites the A sites, or the lattice points, and the B sites the bond points. And the position of this RP is x1 d1 plus x2 d2 plus x3 d3, with a constraint that x1 plus x2 plus x3 is equal to 1. It's actually a very nice way of expressing things, and those who live their life in graphene use it all the time. It usually takes me a few minutes to do that. The A's here just show the standard directions for a triangular lattice. So A1 is along the horizontal direction, and A2 and A3 go off along the 60-degree angles relative to the others. So, okay, so that's the geometry of the model that we want to look at. What? Oh, somebody dismissing me down here. What's going on? Oh, okay. So now what are the requirements for making the model? One is we want 1 variable per site, which we're going to call Z of RA. So Z, remember that we're thinking of the red dots as the sites. So Z of RA measures the height, the vertical height of the site, the particular RA site. So RA are the set of sites that are red, and RB are the set of sites that are blue. So, RP is a rotational pivot point, as I said. Rigid rotations about R leave, oh, you know what? Shoot. I guess you can see everything. I didn't realize that they cut off quite so much over here. So what for rigid rotations about the pivot point, this combination of the z's is 0. So that would be, no energy cost. And if this is non-zero, the tri-bond energy is a quote, kind of an elastic constant times the square of this quantity right here. So it involves 3 heights instead of 2. And the energy is non-zero if 3 sites in a pivot point are non-coplanar. Okay. So I guess this is yeah, I did this all last night, and I probably made some mistakes here. This is exactly what we said before, but here I've expressed ERB in a slightly different form and U in a slightly different form. That this is, it's quadratic, and it depends on the RB. So that's like what we have in the lattice models we've been looking at, where the RB sits at the center of the bond connecting 2 sites. Here, the RB sits at the center of a bond that connects 3 sites. And the rotations about RP are leave ERB unchanged. That's when we have 0 energy. Okay. So the ERB is the sum over the xi's of the height of the site that sits at RA, but RA sits at a site RB plus one of the DIs. So here we're summing over all of the DIs about a given bond. And again, the energy is that. And a displacement of the bond is DI, which is where it starts at. That's relative to an RB. So this is an internal coordinate. And it has the height function, which is zi with a unit vector in z, and you subtract from it the RP because we are doing we're pivoting about that point. Oh, excuse me, I forgot to unplug the telephone. And you can see that that if I take the 3 U's, U1 cross U2 dot E3, U3, that cancels out the D's and the RP's, and it actually is equal to this bond construction. So, if the U has both a component that is parallel in the parallel surface, and it has a Z component, and you put those all together, and what you want is to have all of these be 0, and since U3 is in the perpendicular direction, what it's doing is requiring the displacements here to be 0. Okay, so now we're going to define the tensions. The T is just the derivative of U with respect to the 3, the tri-bond, and that's equal to KERB. So this is 1-to-1 correspondence with what we have in the 2-dimensional, or the 2-site system, the bibond. And the force, which is exerted on RA, is the derivative with respect to the displacement. And this we found, you can calculate it out. It is equal to the sum over I again of the set of xi's times T of RA minus the site minus the vector DI. And you can see here that the vectors DI, if I have a site here and the vectors DI point like that, you can get, the sum of them around there are, given what this is, you can do the calculation of what this site is relative to that site. Okay. So now we want to have exactly the same things we had before. We claim that E is equal to a matrix times Z, only in this time it's a scalar. And of course, we know that's already true because we defined E to be in terms of the Z. So we certainly have a vector that's taking E of RB and relates it to the Z of RB, or Z of RB transposed. Oops. The tension, again, in analogy with the two-dimensional system, is equal to the elastic constant times E, and the force is going to be a matrix times T. Well, clearly from what we've had on the previous page, C of RB and RA, you need them both, is the sum over the xi of RB plus DI RA. And if I plug that in and into an expression like this, and keep track of the sums here, this multiplied times Z gives you exactly what we had before. The Q is the same thing because we had T. T depends upon E, and E we know depends upon Z. So we can calculate the force in terms of Q and T. So you can see just by looking at this that the sign change is here, and these two things are indeed matrix transposes of each other. So then we have the same thing as before. We can introduce a Fourier transform. So E of Q is C of Q times Z of Q, and F of Q is capital Q of Q times T of Q, where C of Q is E to the I, sum over the i's of xi e to the I Q dot di, and that's equal to Q star of Q. So we now have the energy we can express either as we did at the beginning, as the strain squared, as the height function squared. So this is the analog of the u du in the two-bond case. Or we can replace the E by T over K and get this. We have the same thing then that, since globally and locally, we have, they're taking the Fourier transform, excuse me, boy, I don't know what that is. Clearly, this set of functions here has exactly the same flavor as what we had in the standard lattice case. So we have N0 is a mode of zero energy. S is a mode with a force on it. N is the number of sites, and NB is the number of bonds. And since we can Fourier transform here, we have the number of zero modes in each Q minus the number of states of self-stress in each Q is the number of sites in the unit cell minus the number of bonds in the unit cell. Okay, now what we're going to spend most of our time on here is trying to derive the phase diagram. Now, this is something which we had difficulty doing with the Kagame lattices and what was the other one we had difficulty with? Well, I know the square lattices that gave the Weil points. It's very difficult to do that thing. But here you can do almost everything analytically, but you're using exactly the same ideas and approaches that we used for the standard lattice. So this is in the X plane. The triangle, the dotted triangle here are the lines for which X1 is 0, X2 is 0, and X3 is 0. The dark gray areas, these gray areas here and here, are regions where there are possible positions of Weil points. So these dark ladders and the light tan. So the light tan and the gray areas are possible. I should say that this is the Brillouin zone. That you should know that with the symmetry points. Everybody who's worked on graphing knows that K and minus K are different, and you have M1, M2, and M3 are symmetry points in the lattice. So this thing is set up so that Weil zero modes in this region map onto the the light brown maps onto W1. In other words, the set of vial sites that are in here correspond to this part of the phase diagram. They only, to get into this part of the phase diagram, which is, this is really dividing up the space of the x's to tell us what values of x give us what kinds of phase. So the W0 is a phase where we have pairs of vial modes. Now, that you have to have in order to, there's sort of a conservation law for the zero modes. They are bred, birth is given to them along these red lines. So along these red lines, you have a pair, all along a pair of sites that have zero energy. Up here, we have the same sort of topological lattice that we discussed for the standard lattices, and the polarization vector that, or the topological vector, as I mean, and it's the analog of what we call the topological vector for the, again, the standard lattice, and it can point in 3 different directions. And everything out beyond this this triangle has the, okay, let me say it different. So that often when you have the equation x1 plus x2 plus x3 equals 1 in this representation of what goes on inside of triangular regions, here, the region for which the x's are 0, all of the x's are positive, is inside this triangular region with the dotted lines. When you go outside of it, the pivot point moves outside the area of the particular triangle that you're talking about. So, here the pivot point sits inside, but if I make x1 plus x2 plus x3 equal to 1, but one of them's, suppose I make x1 equal to -1, then it moves this RP out in this direction, and we have a pivot about a point that's outside the triangle. So the brown area maps into W1 here. This, he's just highlighted that so you could see it. There's a similar 3 and a 2 area. So the 2 takes you to over here, and the 3 takes you to over here. Throughout the white region, we have topological lattices, but some of the distortions become unphysically large. Okay, so we have what happens to the dark and the brown areas. For each blue point in A, so this is A, and there are, for each blue point in A, what happened to my blue points? This is A, I'm sorry. For each blue point in A, there is a red point in B containing a degenerate vial points, a pair of degenerate vial points. So here, for each time we have here, when we get to this point, it corresponds to a degenerate vial point in B, which are the red sites. Okay. The regions with arrows are fully gapped, as we said, the topological edge states, and along each red line in A, there is a red point in B, okay? This is what I copied from our notes. We wrote this a couple of years ago, so I may have forgotten a little bit of it. Well, the red points, I think it's got this backwards. The blue lines do something here. For each blue point in A, there is a blue point in B containing a degenerate point. Okay, we'll go back and I think derive those results now. So so what are the 0 points? The 0 points are when C of Q is equal to 0, and C of Q is this function, which we really wrote down before. C of Q has the xi's, and you have when you sum over them, it becomes this, and that we have the appropriate representation of that all the way out. So this is satisfied clearly at the K points, where Q star is plus or minus QK. And the plus and minus K points are different, but there are only 2 of them. So for example, I can take x equals 1/3, 1/3, 1/3, and that puts you at this center right here. And you can calculate that what qk is the 4 pi over 3a in the x direction, and the e to the I qk dot dj for the set of, the three dj points. You get this exponential, and we know that the sum of these three things, e to the 2 pi I over 3 to 2 pi ij over 3 summed over j is equal to 0. So now, because C of Q advances by 2 pi as Q wraps around Q star, so when we look at I'm not thinking myself clearly today. The contour integrals around points that have a 0 or an infinity in it, we get 2 pi. And so if we look at a region around the 0 point here, it has to be continuous around there. There's no discontinuous change by saying that, well, if I have this x 1/3, 1/3, 1/3, I can get a different value of the topological result, which is, the topological charge for this thing is 0. If I have 1/3, 1/3, 1/3, it has to exist over a wider region. Therefore, there must be a Weyl phase in a finite region around the 1/3, 1/3. I see I put the wrong thing up here. I'll do it here. So we're talking about x 1/3, 1/3, 1/3 sits here, and so that means we have to have a finite region, and this is a finite region, but we can do better and get more about that. If we look at the point x equals 1, 0, 0, or 0, 0, 1, there are no solutions to C of Q star equal to 0. I mean, all you have to do is to put x1 equal to 1 here, and there's no way I can get 0 when I get rid of those things. So if we look at these points, right, these are points where we know that we don't have any solutions to C of Q equals 0. So that they then represent the boundaries, and the line x2 equals 0 passes through there, and it turns out that this is also the meeting point. Well, this is the meeting point of two of them. So this is along the line x2 equals 0, but we also have, even when x2 is 0, we still have regions where there's no solution to C equals 0. For example, I could have, I could have a combination with x2 and x3 only that makes this 0. Okay, so did I finish here? So and what that means, it is clear that for these, there are no solutions, and there must be a gapped phase in the vicinity of the three corners of the dashed lattice. So that means because we have a 0 here that doesn't have any of the Weyl modes, we must have a finite region around it, and that foretells the existence of these polar phases that have a quote dipole moment. So for x equal, there are no solutions to C of Q of x star equal to 0, and there must be a gapped phase in the vicinity of the three corners of the triangle. This depicts a Weyl mode for the point at the 0 origin here. So what that means is that we are allowed to rotate freely about the yellow point, which corresponds to the center of mass of the triangle. And you can spend a few moments looking at this. If we rotate this one, well, clockwise or counterclockwise about this line, notice that what that does is it leaves this unmoved, but since I'm rotating about this point, it raises that point. And then we go and we rotate about this point, that lowers this point. And then we come back to this guy, he's going to rotate about this axis, and that leaves this point untouched, and so on. So down here, we're doing the same thing, and it gets repeated and repeated. We have a construction here where each of the hexagons that go with the honeycomb lattice has 3 pivot points and has one going up, one going down, and one not moving, though the up and down ones change as you go along here. So we always go, down, up, down, up, down, up, etc. So this is a construction of a zero mode that exists at the center there. Okay, so Weyl points can only disappear if 2 of them meet, and this must occur at one of the time reversal invariant points, M1, M2, or M3. So I really didn't transfer the right ones over. So M1, M2, and M3 are these 3 right here. And these are the points at which the Weyl points go to their death. So the M points are time reversal invariant, and they have this property that the 2 solutions you get, Q star, when Q star is equal to minus Q star plus G. See, that's really Q star plus G is really the same thing as a minus, but we're moving around the Brillouin zone, so we can put in the G in place of not having it. So this is what QM is for along the direction D, and we can take the dot product here, and you find that CQ is equal to 0 for this type of configuration if 2 of the X's have a minus sign with it, and one of them has a plus sign. So you have 1, which is 1, and 2, which are minus a half. And so these things, the X equals a half, which is the same thing as XK minus 1 and XK plus 1 equals a half. These define the red lines in the lattice. They are the ones that are at the boundaries between having Weyl modes and having some other state. Actually, it's the boundary between Weyl modes and, in all cases, between the polarized modes. Okay, again, the points outside the dotted triangle have a pivot point that's outside that triangle. Okay, so what happens to the Weyl modes? When the X point is in the 0 region, so we go back to here, when an Weyl point is in here, they reside if they're in W0, they reside in these dark regions right here. Now, you should remember that these lattices, this is just the first unit cell of a Bravais lattice, of the reciprocal lattice of a Bravais lattice. So if I have this point over here is connected to this point, I think it is. This is K and minus K. So if I sit on a point here, I go to a point down here. And if I sit at a point here, I go to a point down there. So you should think of these 2 regions as being connected. In fact, they're all connected in some sense that I can turn them, well, not all of them, but a couple of them here. So a pair passing, starting in, say, the K1 region, that's up here, I mean the M1 region. Yeah, so they go to the opposite one. So this guy, traverses, we start at this point, some point in here, and I come across to the other side, and what they will annihilate at the M+1 thing. So I can go to, I can't, once I'm in here, I need to go to one of the other points to annihilate. So to go continuously, I need to do that. Though I guess I could always go back to here and annihilate again, but they can also go through a more complicated path where they annihilate at the other M's. Okay, so again, outside the W regions, the spectrum is gapped everywhere. there are 3 disconnected regions, and then you can see they each have a different polarization. And so that makes them different. And now we do exactly the same thing that we did before. We can just think of the simplest one. Suppose I have only one x. The c of q then is e to the I q dot d. So we think of this c as being associated with the displacement vector d sub j. So this is a c sub j really. And it has an x which is only in the j direction. So this, if this was a d1, then the x1 out here is equal to 1. So then we can calculate for the particular vector dj what this integral is, and it is the reciprocal lattice vector bi dotted into dj with a minus sign, and we can now calculate what the topological polarization is simply by calculating n1 and n2, which is all that we need to do. This is going faster than I thought it was. Okay, so now that we admit different values of x, let's think of another zero mode. So this one, we put x at 1/2, 1/2. It's much easier to see the zero modes at these symmetry points where I don't have the arbitrary x's. So that means that the pivot point is right here at the edge, like that, and it can rotate either going like this or like that, because we can pivot in 2 directions about this point. So now let's see how this goes. Go counterclockwise around this line. So what that does is it raises this site and lowers this site. So that means that this guy has to rotate in the opposite direction because we want to get this to lower, and this goes up. So we alternate plus, minus, plus, minus, plus, minus. And notice that when we do these rotations about this point, we leave that point untouched. And then we come down here and we have the same thing. Now we are, in principle, you might think that we're rotating about this site, but we're not really doing so. This is just coming up, and what's happening is that this site we're rotating it about this direction as opposed to this direction. So, but now when we go beyond that, I don't have to do any more because I'm rotating about lines that are along, a line along here, and I'm never going to do anything to change the position of the red dots along here. So the red dots stay where they are, and the same is true up here. The red dots stay where they are because that's fixed as I rotate about this axis. So we have a line of zero modes, and you can see here, this is what CQ is. If I set Q x equal to plus or minus pi, plus or minus pi, this guy goes to 0, and that's what the zero mode is. So they put them all together. Okay, now edge states. So what do we do for the other lattices? We cut bonds along the side here, and we found that for the Kagame lattice, for example, that we had to cut 2 bonds. The bonds were straight lines to open up the torus coming from the periodic boundary conditions. And so we had at least 2 bonds, and in some cases we had 4 bonds and 2 sites that we took off. Here we can take out one line of the bonds centered on the blue points, and we've immediately opened up the circle or the torus like that. So when we do this to open up the edges, we remove dn bonds, but no sites. The sites are still there. This site right here, really I should think of as being connected to over here. So how many zero modes and states of self-stress do we have? Well, we have the number of sites don't change. So the only thing that changes is delta NB. So we have here that ends. So what he's thinking is that delta NB is negative if we're taking away a bond. So when you write n naught as minus s equals delta NB, remember that the Maxwell-Caledine equation is n naught minus s equals dn minus nb. dn is fixed, and so we have minus a minus delta nb, which makes this number, the delta nb is a positive number. And of course, it's valid for each value of q. So we have that again, and we have the same setup as we had before, namely that n0 is RT plus RL plus d over 2 pi, and GL, RL rather, is the local value of the the R tensor here, or the R vector here. And in the end, it's just the polarization charge on the edge from +1 on A and -1 on B. So if our edge is pointing upward like this, the dipole moment is going to be +1, -1, and it should be then, the dipole moment here should be minus d1. d1's the upper direction. And when I go to the downward direction, where the outward normal to the surface is d1 downward, which is minus d1, up here it's, well, the dipole moment, I think, is downward here. Let's see, this is plus and this is minus. So when we go from minus to plus, or plus to minus for we go, I've even forgotten elementary electrodynamics. The dipole is the, well, we have it here, just a second. Yeah, so this is, it's minus to plus here then, okay, that you go from minus to plus for the dipole. So if we look at the upper X surface, the upper topological charge is plus d1 for the reasons I just told you, right? That the vector points from there to there, d is that direction. The normal to the surface is is in the plus y direction, and there should have been a parentheses here. The √3 is in the, and √3a is in the denominator. And the values here have to do with the spacing between the layers, and that comes from the fact that if this length is a, then the total length here is a over √3. The total length is √3 times a. That's this distance. Okay. And the contribution to the zero mode is in the x direction here from the upper, from just calculating the d1.g with a 2 over 2 pi, we get 2/3. So it looks like we're headed towards fractional values, but we still have to add the topological charge, and the topological charge, of course, depends upon our choice of unit cell, and that is going to be a compensate for us. So if we go over here, there are 3 different values of RT that we find. It's minus G1, minus D2, or minus D3. If it's minus D1 with a surface that is along D1, then the topological charge here is minus 2/3. So we have a zero charge, or a zero, no modes of zero energy for this configuration on the top surface, the upper surface. And this, for the RT, then we have RT is minus D2 or minus D3. This is the upper surface for the same as this with D2 or D3, and you can see that, oops, that's the wrong one. Yeah, you can see that we have D1 is like this, and we have minus, so we have a D1 upward and a minus D2, D3 downwards, and what that does is to give me plus D1 dotted into this, and that gives me 1/3, which then tells me that the contribution to the total charge is 1/3. So we now have the topological charge plus the constant upper line local charge. I get M0 is 1. If we look at the lower surface, then RL is minus D1 over 2. And of course, since you dot RL into Q, then you know, any three, either of these vectors, either minus D1 over 2, or because, you know, we're dot producting this into the minus G that points downwards. So the dot product of that with either of these three vectors is the same. So you might as well just use minus 1/3 D1. So that gives us that M0x is 1/3, not 2/3. RT, when RT is minus D1, M0T for this one is plus 2/3. So the total M0 is the sum of those is 1, and we get what we want. There is, you know, unlike the standard lattices, the Kagame lattice, where we broke 2 bonds, here we only broke 1 bond, as we said. And so the total number of zero modes on the surface, on the 2 surfaces, is 1 and not 2. And you can see why that is. There is an asymmetry between the top and the bottom surface. The bottom surface down here has, you know, all of the T2 and T3 pointers, and this surface has the T1 pointer. So we have an asymmetry between the top and the bottom without even doing anything exotic to the topology of the system. Yeah, so notice that we change topological classes here by moving the pivot point, but without changing the lattice. So for every one of these lattices, we have 1 removed, and there's going to be, if we are in a polarization state, then we're always going to have 1 zero mode, which is either on the top or the bottom, or the right or the left. Well, actually, the right and the left, which I didn't write out here in detail, you've actually cut 2 bonds per unit cell. So the unit cell now is the 2 triangles together, or maybe these 2 triangles. I mean, there are 2 choices you can have, but you can't take just this or just that, because that doesn't give you what the unit cell on the surface is. So the unit cell has, has twice as many zero modes, and indeed, you're going through exactly the same calculation, which is well defined. You find that M0R and M0L are 1, 1, and that's for the case where there's stuff here where the unit vector is along the, I mean, this G changes to 90 degrees, and one of the D2s or the D3s, yeah, okay, I've forgotten exactly the details of how that goes, but this is what the calculation gives. We have the 2 choices, 1, 1, 0, 2, or 2, 0, and that's not too different from what we were getting in the Kagame lattice, where on the vertical line, we had 6 sites per unit cell instead of, wait, no, I still had 3 sites per unit cell, but the unit cell was twice as long. Okay, so that is approximately all that I have to say about this particular problem. I certainly gladly entertain questions now, but if we still have a little time left after that, I want to just show you briefly the results of the calculation of what happens when you go to finite temperature in the lattices that have a line of 0 modes, okay? So, any questions?
Are there any questions? Okay, let me pass the microphone.
Okay, Professor. I'd like to know about topology. How do you classify topology in these contexts? Let me make it more precisely. In elementary state solid theory, you have an electron moving in a lattice. You have the energy spectrum of this electron, that's energy bands. And then you know topology, more or less, the topology for the bands of energy, energy bands. In this case, you have phonos, I think, vibration, more or less similar to that problem for electron moving in a lattice. How do you classify topology about what number? Is about the Sher number, the Potragno number, of what? I'd like to want to know more precisely the topology on
Boy,
on
I'm
this
having
contest,
trouble
please.
understanding again. So there was a question now. Can you?
Let me make more precisely. What is topology in this context?
Well,
Because in general, topology you classify by why the numbers, the topology for curves, for surfaces,
I mean,
the Gauss number, and there.
So it's topological because it has to do with this basically the same group as the Su-Schrieffer-Heeger model, and what we're doing is we're picking up a number that doesn't change as we change parameters in the system. So there's a characteristic of this system that it always has in RT or an RL that doesn't change as we go from, as we do slight maneuvers to the system. So in this case, as we move the pivot point about, we do not change the quantum number that comes from doing the integral of the determinant of the compatibility matrix, which we still have. So, I mean, that's the sense in which I consider topological, that there is some protected thing by this. Well, the thing that's a little different about this is, and it's true of all of these topological things, is that it's not the symmetry of the lattice or that tells you whether or not you have a topological charge. But so, I mean, I appreciate your question, and this is actually an area that I have not delved into too deeply, because I get away with doing the simple things. I don't have to tell you exactly which group I'm dealing with, though it's the same group that you deal with when you deal with the Su-Schrieffer-Heeger model. And obviously, it's just maneuvering around the complex plane. It's not as complex as the topological points in graphene, where you have 2 degrees of freedom, or you're working on a surface of a sphere instead of the surface of a circle. It's right.
Thank you, Tom. More questions?
Yeah.
No, I think you can go ahead.
Okay, so what I want to do is just show you, we have, oh, I thought it was 10:40. We have lots of time. Again, I apologize for not having more to do, but that's the way it goes. Okay, so what I want to do is to pull up. So here's, I'm just going to tell you the results. I can't, this was done several years ago. But so what we're interested in is, if we take the pure square lattice, we know it has these 0 modes running along the 2 axes, along the qx equals 0 and the qy equals 0. So that means that we have 0 modes. It's certainly going to disrupt stability. But of course, it's also true that when you have modes that are near 0 in energy, their contribution to the fluctuations are much larger. So one can expect to have, at finite temperature, a larger contribution from fluctuations than for other systems, because the energies are so low. So if you look at the square lattice itself, then you have all of these, without any next nearest neighbor bonds, just nearest neighbor, you have all of these, straight lines that can buckle. So you can take any one of the lines and pull it this way, and to linear order, to linear order in a displacement, you don't get any, you haven't disturbed anything other than the one line. If I pull it a little bit further, of course, then the unit cells along the x direction get smaller in height, and you can have these fundamental excitations of the system, and you have a number of different configurations that are possible, that scales like the length of a side or the perimeter of the sample. So all of these states that I've shown below here are the same energy, and at zero temperature, that's just the way it is. But you can ask the question, if I go to finite temperature, is any one of these configurations preferred over another one? And the answer is yes, though you can do some switching back and forth. And that's what the people call order out of disorder. The disordered fluctuations give you more entropy in, say, the D version of this lattice than the E and the F1. And so you'd like to write down a model that produces those results. So what we did is to look at a model where I have a nearest neighbor potential energy that goes like x squared, and a next nearest neighbor one that has a kappa in front of the x squared, and it gets stabilized with a g to the fourth. Now, if I look at this system, if kappa is 0, and even if g is non-zero, we get basically 0 modes there, because this is a fourth order term and it's not contributing to the harmonic, the calculation of the harmonic order, unless of course you've stretched. And if you stretched, about your reference state, then you need to change things and make sure you get that all straight. So anyhow, the model we used is these two things are present, and we ask what happens in a phase diagram where we have, let's see, can I make this even larger? Full screen. Okay, there we go. So this is a phase diagram in the temperature kappa plane. At 0, we have the lines of 0 modes. On the right, you have a stable lattice in which the shear modulus, which is proportional to kappa, I guess I should have mentioned that up here, that nearest neighbor bonds are in this configuration are never going to give me a shear modulus, because I can just keep on going. So this shear distortion is the guessed Hutchison mode for the system. Okay, so now back to this. So what we have is a mechanically stable lattice in which G is proportional to kappa as long as kappa is non-zero. We hit here, and the entropy contributions, the fluctuation contributions, as I cross this line, become larger than the mechanical one. And your shear modulus, actually, with calculations we do, and I will not repeat them in detail because they're fairly complicated and I've forgotten the details. This is goes as t to the 2/3. You go further, and then you're headed towards a rhombic phase. So the rhombic phase is the one where you have the sheared configuration. So this C shows the Monte Carlo calculations that were done. In the square lattice, you have absolutely vertical lines and horizontal lines. Here, we have a region where we have very strong, simply one phase. And then there appears to be a grain boundary that switches a little bit and then takes you back. And then there's a grain boundary along here. But it takes a lot of work to get these Monte Carlo things to give you what you want. But really, this is in the end what we got. So it's pretty clear that with the Monte Carlo, the system prefers the slanted to the unslanted. You've got an order both of the fact that you're not flopping all over the place and that you've gone from this to this as a preferred port. So now, how do you go about doing a calculation like that? Well, the first thing to observe is that there are other systems that have these zero sort of lines. So there is this model that Berezhensky, no, was it? Let's see, I've forgotten the name, Khmelnytsky it was, who asked the following question. Suppose I want to look at a phase transition from a fluid phase to a crystalline phase. And I would like to consider a theory where it is, it's almost a second order transition. So what you can do is to say, let me look at S of Q, the structure function of the solid, of the liquid in the liquid phase. And as you know, it has peaks that go like this. And there is one peak that corresponds usually to the nearest neighbor of the atoms in the fluid. And it grows taller and taller as you approach the solid state. So let's write down a model in which you don't put in the n cubed. So if you write down a mean field-like model for the solid transition, you can write down, it's 1/2 rho squared plus a rho to the fourth, but you can also have a rho cubed term. And then you say, let rho be a sum over reciprocal lattice vectors q of e to the iq dot r times a rho of q or rho of g. So Khmelnytsky did that, and he asked the question, well, suppose the fluctuations are large enough because I've got the inverse of the structure function has almost a zero there. And so he set up a method of doing that, and it can be applied to systems like this. It works beautifully for the square lattice with the zero, and I think Xiaoming, she can tell you better, went on after we did this work to do another lattice which has a different symmetry. So what you want to do is to pick up the determinant of those fluctuations, and there are lots of different things we had to worry about that. But I mean, fundamentally, the answer is yes, that soft mode does get, it has an impact on what happens at finite temperature. And in fact, it stabilizes the system in two ways. One, you have a change in the existence of the shear modulus. And then you also stabilize a particular one of the many different phases that you have. This anomalous regime probably has lots of those back and forth things.
Okay, can I ask something quickly? Tom, in the green region, you have a finite shear modulus even at 0 kappa.
Well, okay, at 0 kappa, that's absolutely at 0 temperature, and you have nothing. Yeah, I mean, you have all of the instabilities we talked about. And as you move up away from kappa, there's always a region where first you are, at small kappa, you're going to see the mechanical system become stable as you stay at low temperature. Fix the temperature a little bit, and you will have a kappa there. But you're seeing fluctuations all around in addition to the stuff that stabilizes the average of this. So you notice, the G goes to 0, T goes to 0.
Okay,
so
okay, no, that's good. Yeah, thank you.
Yeah. Any questions about this then? So I made it in an hour instead of an hour and a half. I do apologize, but I thought I had so much there that I talked too fast. Yeah. So
you finished? Sorry.
This is all I really have to say now. Yeah, I apologize for not having.
No worries, no worries. Let's thank Tom again. Are there any more questions? Okay, thank you so much, Tom, and thank you very much for all the lectures. And we have coffee break now, and we'll be back at 4:30. Okay? Thank you, Tom.
So, Danilo, how many people do you actually have attending in the auditorium? 30. That's pretty good. That's not so bad. How many people are? So how do I get a hold of the copies of this? Can I just do I have the link? Okay, right. Is the link on the web page? Okay, okay. Uh, I see.